Laurent was in occasion of an international meeting held in Brussels in 1875. We were there because Chaim Brecis and Roger Temam were main speaker, and then many people working with both, we were there, among them Edia Touch, Alain Lamien, Alain Arnaud, et bien sûr Marie-François et Laurent. And in fact, during this time, we make a lot of excursions, and if I am not wrong, it was one of the first occasions in which Marie-François and Laurent meet. After that, we share many participation in other international meetings like Besançon, and at that time we were starting our first joint paper concerning Khrushchev type solutions for quasi-linear equations with absorption. And I remember very well the very good time that we share making mathematics and also making tourism, because I win a position as full professor in the north of Spain, and then I spent 2 years in Santander, and Laurent came quite often, and this is my family. And in fact, they came to Madrid in occasion of the first France-Spanish colloquium on nonlinear PDE. You can see both of them at home. And then we started, Laurent and I, a series of papers concerning the energy method in order to apply it to porous media type systems and higher order equation, so without the maximum principle. And then it was the time in which we make many contact with the Russian school, and then in particular Robert Kessner organized in Visegrad in Hungary a very nice meeting where it was also Donald Aronson, Maslov, and Olga Olejnik. And we were there, we enjoyed a lot, and Susanna Kamin was also there. We also shared many other meetings. I remember very well the meeting at Oxford, another in Paris. And also I have the opportunity to visit them for 1 month. And then it was a wonderful time in which I meet the family of Laurent and Marie-Françoise, Frédéric, Fabien, Ophélie. They were marvelous. And we were working very hard in some direction concerning the asymptotic behavior for nonlinear problems with a continuum of stationary solutions. And we have unpublished, but I think it will appear sometimes after some time. And also with Marie-Françoise, we were together in Athens in the Second World Congress of Nonlinear Analysis organized by Lasmi Kantam. And of course, we were together in the meeting in honor to Philippe Benilan. The influence of Philippe Benilan in any of us was really very, very deep, and we remember him very often. And I were there when Laurent was the organizer of the doctorate doctorate causa to Jim Serrin in Tours. It was a wonderful time. And it was organized another conference in honor to Marie-Françoise and Laurent Véron, but I was sick for some period, and to me it was impossible to be there. But I also remember very well the meeting, the workshop that we organized in Tours, and it was the time in which I knew Han, and it was a very, very interesting workshop, and many good speakers were there. I have a lot of many other pictures, but I will show you that for their 75th birthday, I hope. And so the plan of the lecture is will contain flat solutions. By flat solution, I mean a solution such that u and the normal derivative, both of them are zero in the boundary, or at least in a part of the boundary. And this will arise for linear and some non-linear partial differential equation. This is related with the unicontinuation principle. This is why I will start recalling some generalities with concerning the unicontinuation principle. Then I will talk about flat solution in semilinear equations with absorption and fourth terms. And finally, I will spend some time talking on a Schrodinger equation with very singular potentials. Well, it seemed that it was in the thesis by Borel that was the first time in which the unique continuation principle was researched outside the analytical class of solution of functions, and then it was Borel and Poincaré who was in the jury, who started the research of the consequence of this nice property. And some years after, Holmgren and many others started the research of this property in the class of solution of parabolic equation. Then many important authors devoted many researches on that, especially Karleman, Tichonov, Nirenberg, and many others. Let me recall several versions of the unicontinuation principle in our days by taking advantage of this nice paper by Tataru. So consider this elliptic operator, not necessarily in divergent form, with Lipschitz coefficient in the diffusion, and let's say for the moment bounded coefficient in the transport and absorption. Let us assume that the matrix A is symmetric. But no condition, no a priori condition is prescribed on the sign of C. This means that it will have application beyond the Hofstrom maximum principle and some spectral problems. Then there are several versions of the unicontinuation principle. The first one is the so-called weak version, means that if I have H2, because I am talking on a non-divergence form of the operator, such that is solution of this equal to 0 in a bounded domain, and if U is equal to 0 in a small ball, then necessarily U must be 0 identically in the domain omega. And a strong version of this property arise when the solution of the operator are such that are vanishing to the infinity order in some point, when I understand this property in the sense that the limit when R go to 0 of this is equal to 0 for any n. Then the conclusion is that U must be identically 0 in the whole domain. And there is a first version of the unicontinuation principle, is that it's concerning local Cauchy data. It says that if I have a solution of the operator equal to 0, and the solution 1 is, and the normal derivative also 1 is in some part of the boundary, then necessarily U must be equal to 0. Some remarks are in order. Since I am supposing that P is linear, this unicontinuation principle implies that if I have two solutions that are the same in a small ball, then must be the same in the whole domain. this is playing the name of unicontinuation principle. Obviously, strong implies weak and implies the Cauchy data version of the unicontinuation principle. And by working with viscosity solution and a weaker form of the solutions, it can be shown that the principles holds for solution in H1. And also is quite easy to see that you don't need an operator, explicit operator P, but it is enough to have an inequality written in this form. So the properties all under much more generalities. And the assumption on the coefficients, some of them are optimal. For instance, the coefficient of the diffusion must be Lipschitz, but this is not the case concerning the regularity on the transport and absorption term. As a matter of fact, I will talk on the case of a very simple semilinear equation, in fact, a linear equation in which this will false for some certain potentials V, as we shall see. And also the presentation until now is for linear operators. It can be shown that for uniformly elliptic nonlinear equations, this principle also holds, because it is possible to reduce the situation to the case of an associated linear problem. And for instance, this also arises for the P Laplacian when P is less than 2. This is shown in this nice paper by Quoc-Hung and Takak in the Journal of the Academy of Science in Spain. But there are many tools in order to show that this principle, the unicontinuation principle, fails in for many problems, in particular for quasi-linear problems. And I devote almost all my career to put this in a proper way. First, by using the method of super and sub solutions in the same spirit than Chaim Brecis and Philippe Nilan and Mike Crandall, proving that some solutions have compass support under suitable assumptions on the nonlinearities for unbounded domain, but also for bounded domains. It's possible to get a solution that form the dead core subsets of the domain. And also in the spirit of the paper with Laurent Véron and also with Anton Seff and others, it is possible to develop energy method that applies for higher order equation and systems. And this kind of free boundary problems may arise, proving that this unicontinuation principle doesn't hold under suitable circumstances. Now I am working in a problem with Chaim Brecis and Lebovitz concerning the so-called space chart problem, in which some singular terms may provoke the absence of unicontinuation property. But as I will show you, we can build solutions that doesn't satisfy the unicontinuation property for semilinear problems like this one of autonomous nature with two roots. So here I am assuming that alpha is less than beta and less than 1. So this is why I started with this. Instead, to search for countersamples for the unit continuation principle, I think it's better to open mind and try to see for general domain and other equations when or not this property hold. So let me start then now with the study of flat solution for slow diffusion with absorption and forcing terms. So let us consider some kind of porous media parabolic equation with an transport and a forcing term that once that we make a change of variable can be formulated like a more easy way, because for energy this is better, the Laplacian operator with a nonlinear and inertia terms and absorption and forcing under the key assumption that alpha, being positive, is less than beta and less than 1. Then in general, it's well known when I forgot the absorption term, that the dynamic of the problems is quite different according let us talk on this formulation, according the exponent B. So for instance, in the Fujita paper concerning the semilinear case, the pure semilinear case, so m equal 1, it was proved that when beta, this exponent here, is between 0 and 1, all the solutions are globally defined in time. For B in this small interval, depending on the dimension, all the solutions blow up in a finite time. And there are, just for beta larger than this exponent, there are solutions that may blow up in a finite time or persist for, are well defined for any time according the initial data. That was for m equal 1. The case m different than 1 was studied in the nice book by Samarsky, Galaktionov, Kurdyomov, and Mikhailov, and also in the book by Galaktionov and Vazquez. But our problem is concerning non-negative stationary solutions of this problem, as I mentioned you. And what I will explain here is a summary of 2 joint papers with Jesus Hernandez and Javdat Ilyasov. Here, in our approach to this problem, the assumption between alpha and beta is crucial, because there are other papers in which the author considered other cases, in particular the paper by Drabek and Takak, or Cazenave, Escobedo, and Maria Assunta Pocho, in which they consider just the other cases and nothing similar is obtained. We need to work, because the problem involves non-Lipschitz nonlinear terms. We can lose a lot of properties, and then we shall work with the weak solutions, in particular, that are ground states. It means that they have the minimum energy, even in the class of possible weak solutions. So a ground state is a weak solution that has an energy less than any other weak solution. And as I mentioned you, if I pass the absorption term to the other side, this is a non-Lipschitz term that will be the reason of why the maximum, the strong maximum principle doesn't apply. And then we will get, as I will mention you, flat solutions and also solutions with compact support. And this is what we shall study. And the motivation for the consideration of this n-dimensional problem started with the joint paper with Jesús Hernández, in which we studied the bifurcation diagram for the one-dimensional problem. And then we showed that there was some small region of lambda in which there are no solution. Then there are some lambda for which there is exactly one solution. And then for lambda greater than this lambda 0, let's say, there are two positive solutions, but there are a lambda star such that for lambda bigger than this, we have a positive solution, and other solution which has compact support or is a flat solution. This for one dimension, but the situation for n-dimensional problems is much more complicated. The existence of solutions for the case n bigger than 1 can be obtained as a consequence of the paper by Serrin with Gasol and Tang, and Serrin and Xu, because in some previous paper by Kapper and Wong, they study the free boundary problems associated to this kind of situation, and they apply the Gidas-Nirenberg approach by hyperplanes to show that the solution must be symmetry. In fact, they prove in this paper that any solution in the whole space must be symmetrical with respect to some point. Let's imagine that this is the origin, so no other solution can be constructed without the symmetry. So if we are in the complete space, it is enough to apply the Kapper-Wong theory and extend by 0, and then by means of some change of variable, we can will the existence of a weak solution. But the system of flat solution or compact support is more delicate. For this is only for lambda big enough. Sorry, this theory by Serrin and Xu and Kapper and Wong is only for lambda star for lambda big enough. And sharper study was started by Ilyasov and Igorov, but what we want is to identify flat solutions which are stable. Then it's not difficult to see that this kind of free boundary problems, free boundary solutions are unstable in already in n equal 1, because you can use the phase plan arguments, and then you see that the trajectory is quite different for any other related orbits. And then by using the Fibering mappings, it is interesting to introduce for a given solution the fiber associated to this solution by working with the energy applied for multiples of this solution. Then you can create a function phi of u, which depends on this parameter. Let me call, because I am now dealing with a stationary problem, let me call t to this parameter. And then we can analyze the first and the second derivatives of this auxiliary function. And we can see that due to the assumptions that we make on alpha and beta, we get that there are two kind of different solutions, but we need to make a deeper approach if we want to study flat solutions. To do that, we extended the Quoc-Hung identity for the case of less than 1 exponents. And we introduced this functional P of lambda, where now the dimension arises in the coefficient of the diffusion term, 2 star. And what we prove is that if we assume, for instance, that U is C1, and it can be improved later, then this function take the same value that the integral, the -1/2n, the integral over the boundary of the normal derivative multiplied by the normal. Notice that this P lambda is almost the energy functional, but perturbated with 1/n, the gradient square of the solution. And then we can see that the behavior of the solution near the boundary is quite well indicated in this formula, because it is easy to prove that if U is a flat or compact support solution, then necessarily P lambda of U must be 0. But more interesting is that if we assume that omega is strictly star-shaped with respect to some point, then the reversus version is true. So if P of lambda is equal to 0, then necessarily U is flat or as a compact support. Then in order to search the stability of flat solutions, we work with 3 expressions. First, with the energy that we separate in different terms: the energy of the diffusion, the energy of the absorption, and the energy of the forcing term, so that the minimizing energy is written in this way, and the Quoc-Hung energy can be written in this other way. Then, for different reasons, because we are interested in the stability, we shall study not only solutions that are critical values of the energy and that will make 0 to the Quoc-Hung functional, but it's interesting to see when the second derivative in the Nehari Fibering arguments are 0, because when it will separate the behavior of the solution into different regions. Then different pictures can be obtained according to the values of alpha and beta. And it is not too complicated to see that the corresponding determinant is a little bit technical. It will depend on the dimension and the coefficients, but in particular, it may arise a set that is well defined if n is bigger or equal than 3, but it's not well defined. So it's not defined at all for lower dimensions, such that if I am working in the framework that I already mentioned, alpha less than beta and less or equal than 1, then we can find, this is the picture for n equal 3, and a small set of values. This is here alpha, here beta. So look, in this small set, the solution, the flat solution are stable, and here they are unstable. If I consider other dimensions, then this set is each time bigger and bigger. And as I mentioned you, this set of stable solution, stable flat solution is empty for n equal 1 and 2. And this is a consequence of to analyze what are happening depending on alpha, beta, and the dimension. So the interesting case is this one, in which we have the simultaneous vanishing of P, and here the energy is convex. So we get the existence and stability of solutions that has zero normal derivative in 3 dimensions. They behave like planet if you wish, because they are structures that are isolated. There must be symmetric, and there is no flux in the boundary. So it looks like planets if you wish. And concerning the stability, we can get H1 stability for solution for this kind of flat solutions in the framework of post-media type problems, always under the conditions that depend on the dimensions. And to do that, we use Lyapunov type arguments. We prove that the energy is a good Lyapunov function. But for m different than 1, we need to use some Philippe and Ilham papers and some more recent version of this by FNDF and Felic. We can also get nice result on the exact numbers of flat solutions for special domains. So if we consider domains or like this one, which are strictly star-shaped with respect to some points, and they are they contains m reflections with respect to some hyperplanes, then we can show that this has exactly m solutions. So for instance, a domain like this, if I start with an omega like this, then the support of the solution must be necessarily symmetric. So it will be one of the balls. And since there are only 3 balls that can be placed inside the domain, we can prove that in that type of sets with the same equation, there are only 3 solutions. This is the content of the paper that just appeared some months ago in Advances in Nonlinear Analysis. So let me pass to the other subject concerning flat solution for the Schrodinger equation. Let me remember that for the Schrodinger equation, the unknown is a complex valued function, is the matter wave function according Louis de Broglie. We shall make assumption on some external potential. We consider conservative forces, and we know that the norm of the complex wave to the square means the probability density according Max Born. A central question in quantum mechanics is to the question of how to confine or localize the particle and how to measure the linear momentum. Of course, that in general, the answer is impossible, it's negative, and this is the famous uncertainty principle by Heisenberg. And in this direction, alternative to the proof by Heisenberg are the unicontinuation results that you can find in the books by Reid Simon, or more recently by Scoriza, Kenning, Ponce, and Vega, Gustavo Ponce, Luis Vega, in which they prove that the unicontinuation principle applies once that I in the whole space, once that I assume that V is bounded on compact interval or on compact sets. There are also very nice papers by Jaime Brecis and Marcus and Orsina and Ponce that improve a lot of these answers. But let me start even in a more elementary question that is related to the Gamow contribution in 1928 to the Schrodinger equation. He was interested in study the case of a Newtonian or Coulomb potential, but in his paper he was the first to quote that it is possible to simplify the profile of the potential by some other simpler potentials that keep the main difficulties, and they are simple for the treatment. In particular, as usual, we search solutions with separate variables, and then the problems, ones that I simplify for mathematical purposes, and the parameters m and h, and if I call the energy A as lambda, then the solutions leads to the solution of the eigenvalue problem in the whole space associated to this potential V of x. And then this is the way in which Gamow arrives to the tunneling effect. He was the first in proving that the solution for a discontinuous potential like this one behaves very differently to the classical mechanics, and it's because the solution, the particle may enter beyond the obstacle. And very related to the Gamow questions was the infinite well potential. It was related in the case in which the potential take infinite values outside of some interval. And this is today one of the examples that you can find in any book on quantum mechanics. And there are several surveys containing hundreds of references on this problem. And it seemed that this problem was proposed by a physical Mott, who won the Nobel Prize later. He was in Cambridge. And it was when teaching this to my student when I realized that something not too clear was in this theory that is quoted in any book on quantum mechanics. The question is that, well, this assumption that the potential is equal to plus infinity outside an interval can be justified by approaching, by truncating the potential by to a high Q, and then making the limits when Q go to plus infinity, and you can construct a solution. So really it's possible to give a sense to the solutions. In fact, the eigenvalues for this truncated potential go to the eigenvalues that are quoted in the books. This is absolutely correct. But which is not correct is that in the representation of the solutions, here's the energy, which is the eigenvalues. You can see that the Mott and many other authors, and I mentioned you in any book, they prolongated the solutions by zero outside of the interval. But then it's quite obvious that these solutions are not a solution of the whole, in the whole space of the Schrodinger equation, because they are developing Dirac mass delta distribution in the boundaries. So they are not solutions of the Schrodinger equation, and also they looks like a confining potential. They are not exactly doing this property. Then after the Gamow approach, many authors considered singular potentials that are extended outside of this interval by infinity. And in particular, it was Porsche and Teller who proposed very concrete potentials, and also more recently Copper and others work with very concrete potentials that has important applications. Let me remember you that Teller was one of the father of the nuclear bomb. So he was very interested in this kind of confining particles potentials. So I started a program some years ago trying to prove that for some special potentials, we get this kind of confinement of the particle, in the sense that we will be able not to say exactly where the particle is, but at least where the particle is not. So the support of the solution will be exactly in the interval minus RR. And the main conclusion is that the flat solution can be obtained if and only if the exponent, if I assume that the potential behaves like an inverse power of the distance to the boundary to some power alpha, then the flat solution arises if and only if alpha is greater or equal than 2. So I produced several papers, first in one dimension and then in several dimensions. And we extended my approach with Rakotoson, Roger Temam, and my student David Gomez Castro, who now is also collaborating with Juan Luis Vázquez. And also with Juan Luis, we extended the approach to the case of fractional Schrodinger equation with potential which are singular. And we are also preparing a new joint paper, the 4 infinite order flat solutions. Let me remember you that in my first paper, I arrived to the conclusion curiously, by studying more complicated equations, since Schrodinger equations are linear equations, but I started considering the eigenvalue type problem associated to semilinear problems like this with an exponent m less than 1. Then in a joint paper with Jesús Hernández, we were able to prove the bifurcation from the infinity of branches that came from the eigenvalues of the Laplacian without a perturbation. And we prove that once that you take, of course, the first branch are related to the non-negative solutions. And we prove that there exists some critical value of lambda 1 star, such that in the first part of the branch, the solutions are strictly positive, and the Hopf maximum principle in the boundary applies. Nevertheless, for lambda bigger than this lambda 1 star, the solutions are flat. In fact, the solution started to have compact support for other values of lambda. If you consider the branch that bifurcates from the second eigenvalue, then there is a change of sign. And again, in the first part of the branch, the solution satisfies the strong maximum principle, in the sense that the gradient is not 0. But after some lambda star, the solutions are flat and became with compact support, and the same with the other branches. Then by making sharp the decay of this kind of solutions near the boundary, I was able to apply these results for the linear Schrodinger equations, since thanks to these estimates and making the assumption that the potential decay, let's say like a square root of, the square of the distance to the boundary, then I can relate this expression with the solution, and then to use the solution of the semilinear problem as a super solution and also as a sub solution, and then this leads to the result. In particular now, we are able to have an alternative to the Gamov 1928 paper. Now there are no singularity at all, and the solution are confined in the interval minus RR. Let me mention you that there are other approaches and nice paper. There are also other recent paper by Marcus, in which they consider the singular potential like this, but for semilinear problems, so both things, singular potential and also nonlinear terms. In the case n greater than 1, but I am quite short in the time, this can be proven in another different way without passing by the semilinear problem, by using local barriers, and it depends on the, we can show that it depends on the coefficients. The solutions are each time more regular. And in this way, it can be proved that this kind of potential localize the particle, in the sense that we can say where the particle is not for any, for solutions of the suitable potentials. And if the power is not 2, it's a little bit more delicate, but it can be proved that the solutions are arrived to be more than flat, because they are flat to the infinite order. This is the main content of the paper in preparation with Juan Luis Vázquez and David Gomez, in which we prove that the solutions arrive to be in the boundary, they arrive to be very flat and any powers. So the program of to find an alternative to the Gamov property is working well, and is not too complicated to extend the conclusion to the complex evolution problem, because it is possible to apply some kind of spectral decomposition and to pass to the limit. So now there is no ambiguity in the Gamov mode confinement potentials, the ones that we consider suitable potentials. And this is all. Thank you for your attention, and thank you to Marie-Françoise and Laurent for sharing with me so